Hello, this is George Gonzalez from Group 5. Today we're going to be doing question 5 and question 19. So question 5 asks us to consider the group of 3 plus 2.4 NC point charges shown in the figure. What is the electric potential energy of the system of charges relative to infinity? So when looking for the electric potential energy, you're going to need to factor the distance in between the point charges into account. And if you have a system of more than one point charge, then you're going to have to account for those as well. So for this particular situation, we have a formula that goes by U, which is potential energy, over 1 times 4 pi times the electric constant. And we know that the electric constant is 8.85 times 10 to the power of -12. And then we're gonna be multiplying this right here by basically by the charge divided by the distance. And we're gonna include one of these for each point that we have. So we have 3. So we're gonna be including 3 of them just like this. So K times Q1 times Q2 filled right. Okay. And then that's going to be divided by R12, which basically stands for the distance in between charge 1 and charge 2. And we're going to continue by doing plus Q1 times Q3 divided by R1 of 3. Then we're just going to add Q2 times Q3 over R23. Okay, so next one we begin to plug in our values. This phrase right here, the 1 over 4 pi E times the electric constant, is also known as K. And we know that K is equal to 8.99 times 10 to the power of 9, as we have it up here. So we're just going to go ahead and set U equal to 8.99 times 10 to the power of 9. And then we're going to multiply it by plugging in our values here. So Q1 times Q2, up here we know that all 3 of the points are equivalent at a charge of 2.4 plus 2.4 NC. So we can just simply write 2.4 squared for each of the values here. And the reason why I'm writing all the numerators first is to demonstrate how we know R1 to R13 and R23. It's not explicitly said here which distances, which point charges are Q1, Q2, Q3. So we're just going to label that ourselves. So we're going to call this one 1, this one up here is 2, and this one up here is 3. So this right here would be the distance between 1 and 2. 1 and 2. You can't really see that well, actually. Hold on. 1, 2, 3. So the distance between 1 and 2 is 4.0 centimeters. Next we have R13, 1 and 3. So it doesn't really say it yet. So then we're going to do 2 and 3. 2, 3 is 3 centimeters. And then the way that we find the distance between 1 and 3 is simply Pythagoras theorem. So a squared plus b squared equals c squared, which would end up being 16 plus 9 equals 25 square root equals 5. So that's the distance between 1 and 3. 5.0 cm. So then you just calculate this all, and it ends up being 4.1 times 10 to the power of -6. That right there is the answer to number 5. It would be this number right here, this letter right here, B, and it's in joules. Joules, there you go. All right, so for question 19, it is it's basically a concept question. So it asks, a conducting sphere is charged up such that the potential on its surface is 100 volts relative to infinity. If the sphere's radius were twice as large, but the charge on the sphere were the same, what would be the potential on the surface relative to infinity? So if at the current radius of the sphere, the potential on the surface is 100 volts relative to infinity, if you were to double the radius of the sphere, 2 times radius, what would happen? So we know that distance plays a role in calculating potential energy. And basically, the farther away from the source of the energy, the more depleted the energy will be at that final point, in this case, the surface of the sphere. So since it's proportional to the distance, if you were to double the radius, let me write that better, 2 times, if you were to double the radius, there you go, then it would be twice as weak. So you could just simply divide 100 volts by 2 equals 50 volts, which would be C right here. Okay, I hope that made decent sense. And there you go, that's all.